Alright, what we're going to talk about are what's called real numbers. There are two types of real numbers, rational and irrational. And all you really need to understand about each one is that a irrational number, when put into a calculator, gets a decimal that goes on and on and on without repeating. So this type is a fraction that never stops. Pi is the best example. All other numbers that repeat or end are rational numbers. So let's look at and determine whether these numbers are rational or irrational. So if you take 522 and you put it in your calculator and divide that, so 5 divided by 22, you get 0.227 272, and it repeats. So the 72 repeats constantly, and so this is repeating, so this is a rational number. If you put this into a calculator, you will get 9, which is a whole number, so it's also rational. And when you put square root of 56 into your calculator, you get a number that's 7.48331477. See how it continues? So this is irrational. This one is rational. And that's how you classify. Now, right now, you don't need to know about the details of the rationals, but you need to understand the difference between the two, irrational and all right, when we're looking at ordering numbers, on a number line, any number to the left is least and any number to the right is greater. So negative numbers look like they get bigger, but they're actually smaller as they go to the left. And positive numbers get bigger as we go to the right. Now when we have fractions, if they have the same denominator, as these all do, you just have to look at the numbers and see which one's bigger unless it's negative. So the negative 4/3 right here is really a small number in comparison to the negative 1/3, as you can see right here. The 5/3 and the 2/3, 5 is bigger than 2 because they're both positive, so that means the 5/3 is the biggest number and 2/3 is the smallest. And if you look right here, we have the answer, negative 4/3, negative 1/2, 2/3, and 5/3. Now to do a mixture of numbers like these are here, let's change everything into a decimal. So if I put this into my calculator, I get 4.472, and I'm just going to go out 3 decimal places. We already have 4.7, and then 12 divided by 3 is just 4.0 if you want the 0, and then 4 1/3 is 4.3 repeating. Now we can order them from least to greatest. The least one is 4.0, so 4.0. Then our next one, if we look at the numbers, is 4.3, and it repeats. And then the next one we have is 4.47, and our last is 4.7. So it's easy to tell when you make them all into decimals, or we can have fractions that have the same denominator. Alright, to make a fraction out of a repeating decimal, normally if you have a regular decimal, you just put it over its decimal place. But in this case, this continues on forever, so you can't really do that. So what we're going to do is we're going to make n equal the 0.7 that repeats. Then what we're going to do on any equation, you can do the same thing on both sides. I'm going to multiply both sides by the number of decimal places. That's going to be zeros I'm going to have here. So I have one decimal place that repeats, so I multiply by 10. And when I do that, I get 7.7. Basically the decimal point moves over 1. Now I'm going to take away this part. So I'm going to subtract n, and I'm going to subtract 0.7. And by doing that, I get 9n. And then what that does is that gets rid of the repeating part. So now we have 7. And so to solve for n, I divide by 9 on both sides. When I do that, I get my fraction. That's now a fraction that represents this repeating. Now let's do the same thing with this repeating. So I'm going to make n equal the 0.21 that repeats. And so what I'm going to do is multiply now by 100, because there's 2 decimal places. So now I get 21.21 repeating. And now I'm going to subtract out n, and I'm going to subtract out the 0.21 repeating, which is exactly this, what we started with. By doing that, I get 99n. 99. Erase that a little bit. I get 99n equals 21. And then I divide by 99 because I want to get n by itself. So n equals 21 over 99. Now, because this fraction can be reduced, we can divide both by 3, and we get 7/33. And there is our answer. Square roots, we can simplify these square roots if we find perfect squares. 4 and 21 are perfect squares. So basically what we can do is we have 2 squared is the 4, and 11 squared is the 121. And anytime you have a square inside a square root sign, it actually comes out without the square. So this and this disappear. So we end up with 2 over and 11. So as long as you have a square and a square root, they actually cancel each other out. That's simplifying. So let's look over here. We still have the negative sign we have to deal with. So we have a negative, but we also have 7 squared as 49, and we have, I think that's 16 squared is 256. Yes. So once we have a square and a square root, they basically cancel. And so we end with 716, but it's a negative because that's still on the outside. And there's our answer for that one. On these problems, we want to find perfect squares that are on the left and right. Well, here are the perfect squares. 1 is a perfect square, 4 is a perfect square, 9 is a perfect square, 16 is a perfect square, 25. Notice we now have the square root of 15 is actually between these two. So if I go to the square root of 9, square root of 15, and the square root of 16, and the square root of 9 is actually 3, square root of 16 is 4, then I know this is somewhere between 3 and 4. 3 point something. And I'll just estimate, since it's close to 16, I'll say 3.7. So let's look at this next problem over here, square root of 130. Well, if I keep going with my square roots, this is 36, this is 49, and we're going to need to skip ahead. We have 100, 121, 144, and now I found 2 numbers that it's in between. So we have, and I'll write this as square root of 121. We have the square root of 121. We have the square root of 144, and this is in between. Square root of 121 is 11. Square root of 144 is 12. So 130 is in between 11 and 12. And since it's right kind of in the middle, I'm going to say 11.5.